So now we start Module 3, and we're going to begin with graphing quadratic functions, modeling quadratic functions. And I will tell you that from Algebra 1, this is about 9 weeks, an entire 9 weeks is spent on the quadratic function, equation, those kind of things. So hopefully this is a big review. If not, well, it's an opportunity to have it a big review. Here we're going to talk about graphing quadratic functions, interpreting what the average rate of change is in a quadratic function, being able to look at a table, being able to identify some of its characteristics, and we'll define those here in a minute. But I'll just highlight here, the average rate of change is nothing more than the slope between 2 points. See that a lot over the course of Algebra 2, it is just the slope between 2 points. Now, the quadratic function, this is the standard form, is ax squared plus bx plus c. C is your constant, and that is also interpreted as your y-intercept. Then you have the rest of your a, b, c, whatever those numbers happen to be, can be utilized here in finding your axis of symmetry. So my axis of symmetry is going to be that vertical line that goes through the vertex. It can be calculated using this formula, negative b over 2a. So whatever your b and your a values are, that will give me my axis of symmetry. Now, if I want to find the actual vertex, I would do that input-output process where I take whatever my value of my x equals, my axis of symmetry, I plug it into my equation, function of, and I put that number into my equation and see what is my output, okay? Abstract here, but we'll practice it. We do it all the time where you put a value into an equation, you come back out with the output. So with that, and I will just say line of reflection, you have your axis of symmetry. It acts sort of like a line of reflection for your function. It has symmetric properties. So just all of this should be a big review from Algebra 1. Understanding what a maximum and minimum is. This is talking about, we did just talk about relative maximum and mins, but this is a minimum because my function comes down, slope is negative, turns positive. Minimum, this is the lowest point of my quadratic equation. Maximum, slope is positive, comes down negative. This is, the vertex is the maximum point. The vertex is the minimum point. Being able to recognize that and understand what those numbers mean. And again, talking about maxima and minimum, which we just talked briefly about in other modules. Now here, being able to graph it. Now, there's different ways to graph quadratic functions, but just using a table, and this is probably one of the more common things that we do. Here is, they give us graph this, x squared plus 2x minus 3. State the domain and range. Well, when it comes to a quadratic function, the domain is always all real numbers. You look at it, it goes forever in positive direction, and it goes forever in a negative direction, so the domain is always all real numbers. Now, if I'm looking for the axis of symmetry, that sort of tells me where to start. So using this formula, I can find out what is my axis of symmetry. So they took and they plugged in, again, this is 1, so that is A, B, and C. So I know as I plug that in, I have negative 2 minus 2 over 2 times 1. So they said, hey, your axis of symmetry is x equals negative 1, which is right here. X equals negative 1. So now I know when I go to graph points and I plot points in my table, I want points to the left and right of negative 1. It doesn't do me any good to come over here and graph, x equals 8. If I plug 8 in here, I'm going to have a huge number way up here on my graph. It's going to do me no good. But if I'm graphing points to either side of my vertex, it allows me to see this shape forming, which is a parabola. Okay, and it opens upward. That's a characteristic that we should know from previous Algebra 2, that since this is a positive value, that it's going to open upward. And if it opens upward, it has a minimum. But being able to come up with that, so then they took some points. Once they figured out what my vertex is, they were able to turn around and say, well, let me just take -2, -3, let me take 0 and 1. And they plugged those values in, and they came up with, this is your xy. And they call it function, right? Function of x, f of x. So this is the x and the y coordinate, because y is equal to f of x. So there you go. And they graph those points, and you can see the symmetry forming. You can see that from my line of symmetry, I have this point that is 2 away from my line of symmetry. I have this point which is 2 away from my line of symmetry. So there we have a reflection. Here we have a reflection, and then of course this point is on my line of symmetry, so it doesn't move. So just, you can be able to visualize those things. And you know, some of you may look at this and say, oh, I can visualize Groot. That is Groot. But no, not Groot. But anyway, let's just go on and thinking about being able to graph. So comparing quadratic functions, being able to look at them and say, what is the difference? What are the characteristics and how do they align? We've compared functions previously, but we were talking about linear functions. So it says compare f of x to the quadratic function g of x with a y-intercept of -1. They didn't give me g of x, so let me put g of x down here. So this would be my g of x, and it says the y-intercept is -1, and the vertex is 1, 2. So that would be x is 1, y is 2. Now, if this is my vertex, and I have a point down here, then I know that it should do this. If this is my vertex, I know that it should be on the line of symmetry, and obviously this is not drawn perfectly. Again, my vertex is on my line of symmetry, so then I know that there is a point equidistant away from there. Okay, so I have a general idea that this is what the shape of my function looks like. And I can see that the y-intercept of this function is possibly -4. The y-intercept here was -1. I see here that my vertex is at x equals 3. So that is my line of symmetry, is x equals 3. My vertex is 3, 5, where here my vertex was 1, 2. I can see that they both open downward, so they both have a negative value, but I can also know that if they both open downward, they both have a maximum point. So I'll just say here 2 is the maximum, so blank has a greater maximum. Who has a greater maximum? F of x has a greater maximum. So just being able to look at those characteristics and compare. But in order to be able to compare the characteristics, you definitely have to understand the vocabulary to what they're looking for. Here, using quadratic functions, ski resort. A ski resort has extended hours on one holiday weekend per year. Last year, the resort sold 600 ski passes and 120 per holiday weekend pass. This year, the resort is considering a price increase. They estimate that for each $5 increase, they will sell 20 fewer holiday weekend passes. Okay. How much should they change in order to maximize their profit? So maximizing their profit, just think about when, this function, as I go up like that and I come back down, this is my maximum point. So I'm trying to figure out where in the heck, what value right here, what value of x is going to reach the maximum y value, right? That's what I'm looking for. That's the maximum, understanding that. So here, how much should they charge? Well, defining the variables, and it says let x represent number of 5 price increases, and let p of x represent the total amount of money generated. So here we have p of x is equal to the price of each pass. Okay, so here's the price of passes times the total number of passes sold. So they said as they increase the cost, they're going to decrease the quantity that they sell. So the p of x, again, is equal to the cost times the number of tickets they sell. They had to do some manipulation here. They had to multiply this out. skipped a few steps. I have it over here. They did the FOIL method, right? They took 120 and multiplied it by everything here. They took 5x and multiplied it by everything here, and then they went ahead and distributed, then they combined like terms, and they ultimately came up with this P of X function. Now they know their value of A is negative 100, B is 1,000, and C is 81,600. So they're able to calculate X, the line of symmetry, which they said is X equals negative 5. So right here, X equals, at the maximum line of symmetry, X equals negative 5. So now if they do that, well, plug that value in here, and when they look at their maximum, it says a ski resort will make the most money with 5 price increases. So they should they should charge $120 plus 5 times 5, or $140 for each holiday weekend pass. And there you go. That's what they are talking about. Now find the domain and range in context of the situation. The domain is somewhere between 0 and 34, because the number of price increases, if they keep taking away the number of price increases, eventually we would have a negative value. So that's why there is a maximum number of price decreases or price increases that they can do, because then they would sell 0 tickets. So right here on my XY coordinate, right here is going to be 34. This is going to be 5. And then right up here is going to tell me, guess what? That is probably $145. So just thinking about that maximum Y value when X equals 5. So here, again, that's what they did. They plugged in the value of 5, okay? And then, so doing the same thing, and I think this is not supposed to be here. But last year, a ticket provider sold, I tell you what, we'll make sure we just do this one in class, but very, very similar to the previous question. Okay. Functions and rate of change. So rate of change, again, rate of change, the average rate of change is going to be slope. And in doing that, we have the input and the output. So f of b, f of a is nothing more than my y values. B and a is nothing more than my x values. So that's what they're talking about. This could be very similar to f of x minus f of x1, x2 over x2, x1. Okay, so that's my y. So being able to calculate the average rate of change. The average rate of change, this indication right here, is the bookends, right? The brackets of -4 to 4. What is determining the average rate of change from -4 to 4? Well, when I plug in to my function 4, they take f of 4, and when they plug it in, they get -9. They take f of -4. When they plug it in, they get -25. So that's why they come over here and they say, well, this would be think about my xy coordinate would be 4, -9. My -4, -25. So there's my x and y coordinates that they plug into the slope formula and come up with a average rate of change, which is what slope is, an average rate of change. So that's what they're looking for here. What else? So if we try to calculate the average rate of change here of this function over the interval of -5 and 5, you want to plug in f of -5, and you want to plug in f of 5, which is nothing more than, I would have -2 times -5 squared minus 5 times -5 plus 7. Then I would have -2 times 5 squared minus 5 times 5 plus 7. Now this should not be difficult for us to do, but this is why we practice this in class too. If I use the calculator and I put into my y equals f of x, right, f of x equals negative 2x squared minus 5x plus 7, and then I look at my table data, my table data will tell me when I plug in negative 5, I get a negative 18 out. When I plug in a 5, I get a negative 68 out. So there are my x and y coordinates. So I can simply take negative 68 minus negative 18 is over 5 minus negative 5. And that should give me negative 68 plus 18 over 10, which is negative 50 over 10, which is an average rate of change of negative 5. Okay, the calculator can do it. We're going to do the average rate of change often, and you'll see it on your state test too, but it's slope. It's two coordinates, you find out the change. What does that mean graphically? This graph looks like this. Okay, it's a parabola, but all they're doing is saying, hey, we have these 2 points, and I want you to figure out what the average rate of change is between those 2 points. Okay, that's it. So understanding that. Now the average rate of change again, using a table, they're saying determine the average rate of change between negative 3 and 3. Between negative 3, there's my xy, and 3, there's my xy. So I just plug in my xy into my slope formula, x2 minus y2 minus y1 over x2 minus x1, and they came up with an average rate of change of negative 12. So again, I just showed you how to find the table using the calculator, and they're saying, hey, if you could look at a table and be able to interpret that, okay? So here, again, testing. Again, here's my average rate of change slope, and it says this table shows the number of students who took the ACT between 2011 and 2015. So take a moment to do this problem, stop, try it out, and then check your answer. All right, so using those points is y2 minus y1 over x2 minus x1. Again, the calculator is going to do it for me. 1,924,436 minus 1,623,112 divided by 2015 minus 2011. This is 4. So I come up with an average rate of change of 75,331. That's what the calculator gave me. Interpret the results. The table shows the number of students who took the ACT. Well, according to this is a positive number. So the number of students who are taking the ACT is increasing by about 75,000 per year. So over the course of 4 years, right, 4 times 75,000 should be about 600,000? No, 300,000. About 300,000. And if you look, we went from 1.9 million from 1.6 million to 1.9 million, which is about 300,000. So, I mean, it seems logical. So interpreting that in the context of the situation from 2011 to 2015, the number of students taking the ACT increased, right? It increased by an average of 75,331 students per year. Okay, so that's the interpretation of it. Finding the average rate of change from a graph. Again, there's a lot of stuff going on in this graph, but they don't care about everything. They're just trying to find the average rate of change between, looks like this point, and this point. They don't care about what's going on in between. They want to know the average rate of change. So you're just calculating slope. But it does say here, the graph shows the amount of money the United States has spent on sports footwear since 2005. So this would be 2005, 0, because they're talking about since that point. Use the graph to estimate the average rate of change between 2005 and 2015. If this is 2005, this would be 2006, 7, 8, 9, 2010, right? Oh, sorry. 2005, 2006, 2007, 8, 9, 10, 11, 12, 13, 14, 15, 2015. So there you go, being able to calculate that information. So we're estimating. You don't necessarily have to calculate this. You could have just rate of change. Um, so the input output, those were my values, x2 or y2 minus y1 over x2 minus x1. Possibly done the 2015 minus 2005, and that would have, the calculator is going to do it all for you anyway, and it would have come up with the correct information because this would have said 10. It would have done it for you. So there we are, calculating that kind of rate of change. So here, doing the same thing again. Stop the video and give this a shot, and then go ahead and check your answers. But let's see here. So it says this shows the television viewers from 2006. So this is 0 is 2006. And it says use this graph to estimate the average rate of change in the Super Bowl viewers from 2026 to 2016. So using the graph to estimate the average rate of change of Super Bowl viewers, according to my interpretation of the slope between these 2 points, I came up with 2.115. And now we were talking about millions. So it looks like from 2006 to 2016, we increased on average 2,115,000 or 2.115 million viewers. So that's what they are talking about in that estimate, understanding. Some years they increased by more than others, but again, we are talking about an average rate of change from that point to that point. So that's overall where we're at. And then solving quadratic equations, and again, this is understanding what the graph is telling me, understanding what my solutions indicate. My solutions to an equation, remember the things, your zeros, your solutions, your x-intercepts, and your roots, they're all talking about the same thing, and that is this location right here, where my function intersects the x-axis is my solution. Now, this equation, they have one real solution because it touches the x-axis at the vertex. They calculated the vertex. Turns out that is where my vertex added is a minimum point, so that is my one solution. In order to get this into a quadratic formula to where we can use that process, we had to get it into standard form. Ax squared plus bx equals c, and that's why they moved everything to one side, and they got x squared plus 4x plus 4. And this would be my a equals 1, b equals 4, and c equals 4. So they were able to come up with that vertex and see what was going on. So understanding the zero of that function is -2, and then the solution of the equation is -2, so the interval would be all values of x such that x is equal to -2. And that's what we're doing. So here, if I were to do this next check, again, stop, try this, and then check your answer. Okay, so here, what I've done is I went ahead and did my relative function, right? I moved everything over to one side, made it equal to 0. I have an a, b, and a c. I went ahead and did my vertex equation to find that x is equal to 12. Now, I know then that what I did was I modified my graph here, but around the values of x is equal to 12, I have y is 0, and then I can see this symmetric value created around 0. So there you go. Here's what my function looks like, and it has one solution of x equals -12. I'm sorry, x equals 12. That is 12. So all of that in the graphing form, so x equals 12. So you know, this is a great tool, understanding what we're seeing and using it for. Two real roots. So here in this quadratic equation, it says find two real roots of the sum with the sum of 24 and the product of 143. So whatever one value is, we know that 24 minus that value is going to be the other value. So therefore, that's how they came up with this, and they sort of explain it here. So when we multiply that out, have 24x minus x squared, and then bring it all over to 0 equals, right? Because we want to have a positive a value, so they moved everything over to the other side using inverse operations. So here's my function. When you did the a, b, and c, they came up with my vertex is x equals 12. And I went ahead and graphed it here for some of our values. We can see that if when x equals 12 down here, that when we graph these points, it looks something like this. So we do have 2 points where it intersects the x-axis. So those would both be solutions. X is 13, x is 11. So those are my 2 possible solutions, and that's what they're talking about. And if we added them together, they sum to 24. If we multiplied them, they would multiply to 143. So that's the process that they're going through. And that's it. So here, a quadratic equation. Find the 2 real numbers with the sum of negative 43 and a product of 306. And I'll give you a second to go ahead and do this, but stop the video, try it out, then check your answers. Okay, so when I go ahead and create that equation, I find out that, again, 2 numbers sum to negative 43, and they are a product of 306. So negative 43 minus some number times that number is equal to 306. Then when I go ahead and move everything over to one side, I find out that x squared plus 43x plus 306. Do my inverse operations, I can find my value of my vertex, and then when I put it into the graphing calculator, I can see that x is negative 34 and x is negative 9, and those would be my 2 numbers that sum to negative 43 and multiply to 306. And here, being able to do that interpretation, which we've been practicing this in class a lot, but being able to do that interpretation here by estimating roots. Estimating is just determining, I don't know the exact value because it falls somewhere between negative 1 and negative 2. It falls somewhere between 4 and 5, and that is my estimate. So as I look here, they put this into the graphing calculator, built a table, and then if the exact roots cannot be found because they do not have an exact value, we can find out where the estimate or estimate where the roots fall. And in this again, so looking at my x-intercept is in between negative 1 and negative 2. So the x-intercepts of the graphs indicate that one solution is between negative 2 and negative 1, and the other is in between 4 and 5. That is just doing a graphing estimate, estimating where my solutions are. So as I look at that and put this next one into the graphing calculator, we can look at the graph hopefully and find out where those estimates are. So just go ahead and graph it and give it a shot. So when I put that into the graphing calculator and I graph it, it looks like my solutions fall somewhere between 0 and 1. And then I have negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 9 and negative 10. So that's where my solutions fall between negative 9 and negative 10, and then 0 and negative 1. And you can see that if you look at tables in this next example, that my value, looking at this table, and we'll do this a lot in class and in explanation, but the value of y went from a negative value to a positive value. So we knew somewhere between 0 and 1, we crossed over the x-axis. Just like here, as I look at this, I went from a negative value to a positive value of y. So we know that we passed over the x-axis, and that's what they're showing you here, is we can interpret that. We can interpret that sign change of my y meant that I crossed through the x-axis. So I know that one of my solutions falls between 0 and 1. So we can narrow it down more and find out where my next solutions fall, but just so you know that that's what we're looking at, being able to do that kind of comparison. And we'll practice more with setting our tables and resetting our tables, because again, it's a tool that we can use, and it becomes very valuable. So with that, we're going to go ahead and work on those graphing and solutions of quadratic equations.